Tonight, we're entering the strange and silent world of venom, where tiny drops of invisible chemistry can stop hearts, paralyze prey, and shape the survival of entire species. Welcome to Sleepy Secrets. In this relaxing documentary, we'll explore deadly snakes, ancient ocean creatures, toxic predators, and the surprising science hidden inside venom itself. Before we begin, leave a comment telling me what city you're watching from tonight. Now, dim the lights, get comfortable, and let's drift into the darkness together. Far out in the deserts of Australia, a mouse steps across the sand for less than 2 seconds before something invisible decides its fate. There is no roar echoing through the night, no violent chase beneath the moonlight, just a brief movement in the dark, a nearly silent strike, and then chemistry begins moving through living tissue faster than fear itself. That may be the strangest thing about venom. Most of the time, it does not look violent at all. It looks quiet. A rattlesnake does not need to overpower prey with brute force, like a wolf. A tiny spider hidden beneath a rock does not possess the strength to wrestle insects larger than itself. Even drifting creatures in the ocean, soft-bodied and fragile, somehow survive in environments filled with predators built like weapons. Venom became nature's solution to weakness, a way for small creatures to suddenly gain terrifying control over something much larger. And evolution discovered this trick unimaginably early. Long before mammals existed, before birds, before dinosaurs, Earth's ancient oceans were already filled with primitive chemical warfare. Some scientists believe the earliest toxin-like compounds may have started as ordinary digestive chemicals or defensive secretions. Over millions of years, those accidental biological tools slowly became specialized weapons capable of interrupting nerves, dissolving tissue, or shutting down muscles. That possibility changes the way venom feels, because venom may not have appeared as a perfectly designed weapon from the beginning. It may have emerged gradually through biological accidents that happened to improve survival just enough to be passed into the future. And once evolution discovered that chemistry could overpower strength, nature never stopped refining it. People often use the words poison and venom interchangeably, but evolution treats them very differently. Poison harms you if you touch it, inhale it, or eat it. Venom must be injected. That single difference forced venomous animals to evolve delivery systems precise enough to move chemistry directly into another living body. Nature invented biological syringes, fangs that fold backward inside a viper's skull like hidden knives, hollow stingers connected to venom glands beneath armored tails, tiny harpoons fired by cone snails beneath coral reefs, grooved teeth designed not only to bite, but to guide liquid toxins into flesh with remarkable efficiency. Some of these systems are so advanced that they almost feel engineered rather than evolved. The cone snail is one of the strangest examples. At first glance, it barely looks dangerous at all. Slow-moving, beautiful shell, quiet. But hidden inside is a disposable biological harpoon loaded with neurotoxins powerful enough to instantly paralyze fish. The strike happens so fast that prey often cannot react before the nervous system collapses. And the ocean is full of creatures like this, which raises a disturbing possibility. In nature, the most dangerous thing is not always the largest predator. Sometimes, danger evolves in silence, hidden inside small, delicate-looking organisms that rely on chemistry rather than violence. That may explain why so many venomous species are surprisingly small. Large predators can depend on teeth, speed, mass, or endurance. Smaller creatures rarely have those advantages. Venom allowed physically weak animals to bypass the normal rules of survival entirely. A tiny spider no larger than a coin can immobilize prey many times its own size. A jellyfish with no brain, no bones, and no visible emotion can stop a human heart using microscopic, toxin-filled cells drifting beneath transparent flesh. Evolution repeatedly discovered that chemistry could replace strength. And over time, venom became astonishingly specialized. Some toxins attack nerves. Others destroy blood cells. Some interrupt breathing. Others create unbearable pain meant to force predators away immediately. A few venoms combine multiple strategies at once, almost like layered biochemical attacks designed through millions of years of evolutionary testing. Yet venom itself is expensive. That is one detail most people never consider. Producing venom consumes proteins, energy, water, and biological resources. For many species, venom is not unlimited ammunition waiting inside the body forever. It must constantly be rebuilt. A snake that wastes venom unnecessarily may place itself at risk later when real survival depends on it. Which is why many venomous animals behave far more carefully than humans imagine. A rattlesnake often prefers warning over attacking. Cobras spread their hoods long before striking. Some spiders fake aggression simply to scare threats away. And certain snakes deliver what scientists call dry bites, defensive strikes with little or no venom injected at all. From the animal's perspective, venom is valuable. Using it recklessly would be wasteful. That changes the emotional picture completely. Venomous creatures are often portrayed like living monsters driven by aggression, but most are actually cautious survival strategists trying to conserve one of the most biologically expensive tools evolution ever created. And some species take this even further by controlling venom dosage itself. Studies suggest certain snakes may inject different amounts depending on the size of prey, the urgency of the threat, or whether they are hunting versus defending themselves. In other words, the animal is not merely biting mechanically. It may be making survival calculations in real time. That level of evolutionary refinement feels strangely intelligent, even if it is driven entirely by instinct. But perhaps the most fascinating part is that venom did not evolve just once. It appeared again and again across Earth's history. Snakes evolved venom. So did spiders, scorpions, jellyfish, cone snails, certain fish, some insects, even a few mammals. The platypus, one of the strangest animals alive today, carries venomous spurs on the hind legs of males. Slow lorises, small primates with enormous eyes, produce venom through glands near their elbows and deliver it through bites. These animals are separated by vast evolutionary distances. Yet nature repeatedly arrived at the same solution. That usually happens only when something is extremely effective. Some scientists now suspect venom systems may be more widespread than humans once believed. There are ongoing debates about mild venom traits in animals not traditionally considered venomous at all. In some species, saliva may exist somewhere on the blurry edge between digestion and primitive toxin delivery. The deeper biology goes, the less clear the boundaries become. And then there is one of evolution's strangest achievements of all: immunity. Certain animals developed resistance to venom itself. King snakes can prey on venomous rattlesnakes with surprising tolerance to their toxins. Mongooses possess partial resistance to some snake venoms through changes in nerve receptors. Honey badgers appear unusually resilient to bites that would severely injure many other mammals. Nature created venom. Then nature created creatures capable of surviving it, which triggered an evolutionary arms race lasting millions of years. Predators evolved stronger toxins. Prey evolved better resistance. Venoms became more complex. Nervous systems adapted. Across immense stretches of time, survival itself became a biochemical competition unfolding silently beneath forests, deserts, rivers, and oceans. And humans entered that ancient war very late. For most of history, venom looked supernatural to us. Ancient civilizations feared snakes so deeply they became symbols of death, healing, wisdom, temptation, chaos, and immortality all at once. In Egypt, cobras crowned pharaohs. In Greece, venomous snakes appeared beside symbols of medicine. Across countless cultures, venom carried an almost mystical quality because its effects were so invisible and difficult to understand. A healthy person could suddenly lose the ability to breathe. Muscles could stop responding for reasons nobody could see. Pain could spread through the body hours after the bite itself. Without biology or chemistry, venom must have felt like dark magic hidden inside living creatures. In some ways, it still does. Because venom attacks the body differently than ordinary injury. A claw tears flesh. Teeth crush bone. But venom rewrites processes from the inside. Nerves fail to communicate correctly. Blood behaves abnormally. Cells begin breaking apart. The body loses control over systems it normally runs automatically. The victim is often defeated not through physical destruction, but through confusion. And perhaps that is why venom feels psychologically unsettling even today. It creates the terrifying impression that life itself can quietly malfunction beneath the skin while the outside world still appears calm. But evolution does not care about fear. Nature does not recognize venom as evil. Venom is simply survival chemistry viewed from a human perspective. In fact, Some toxins now being studied in laboratories may eventually save lives. Researchers have already developed medications inspired by venom compounds for blood pressure disorders and clotting problems. Scientists continue searching venom molecules for new treatments involving pain management, neurological disease, and even cancer research. Ironically, some substances originally evolved to kill may eventually become medicine, which creates a strange contradiction running through the entire natural world. The same chemistry capable of stopping a heartbeat may also help prevent heart attacks. The same toxins that evolved inside ancient predators could one day help doctors treat human suffering. Nature rarely creates things that are purely monstrous or purely beneficial. Venom exists beyond those human categories. It is simply one of evolution's most efficient inventions. A system built not around rage or cruelty, but around precision. And perhaps that is the most unsettling realization of all. The deadliest creatures on Earth often do not rely on brute strength, intelligence, or speed. Sometimes, all they need is a single, invisible drop moving silently through the bloodstream beneath the dark. The sand barely moves before the strike happens. Somewhere in the dry interior of Australia, beneath heat-cracked earth and scattered brush, one of the deadliest snakes on the planet lies almost completely invisible. The inland taipan does not hiss dramatically. It does not spread a hood like a cobra or shake a warning like a rattlesnake. Most of the time, it simply waits. And then, in less than a second, everything changes. The bite itself is almost strangely small, quick, efficient, nearly silent. But hidden inside that brief movement is venom so potent that scientists estimate a single full bite could theoretically kill many adult humans. The toxins move through the nervous system and bloodstream with terrifying speed, shutting down communication between muscles and nerves until breathing itself becomes difficult. Yet the strangest part may not be the venom. It may be the snake's personality. Despite carrying one of the most toxic venoms ever measured, inland taipans are reclusive animals that avoid conflict whenever possible. They live in isolated regions where humans rarely encounter them. In some ways, they behave less like aggressive killers and more like nervous creatures trying desperately not to be noticed. That contradiction appears again and again in the world of venomous snakes. The deadliest species are often not reckless predators hunting humans through jungles. Most snake bites happen because a frightened animal suddenly believes it has no escape left. Humans tend to imagine snakes as symbols of aggression, but evolution usually shaped them toward caution instead. Venom is too biologically expensive to waste carelessly, and some snakes evolved astonishingly sophisticated ways to avoid using it at all. The rattlesnake may be one of the clearest examples. Long before striking, it often announces itself first. That famous dry rattle echoing through desert air is not a hunting sound. It is a warning. Back away. Leave. Do not force this situation further. From an evolutionary perspective, that sound makes perfect sense. A large animal like a human cannot be eaten by the snake. Attacking us carries enormous risk. Even a successful defensive bite could end with the snake crushed beneath a boot or shovel. The rattle became a survival tool, designed not to begin violence, but to prevent it entirely, which makes the rattlesnake feel strangely misunderstood. Its venom is devastating. Hemotoxins destroy tissue, disrupt blood clotting, and damage blood vessels with frightening efficiency. Yet, the snake itself often behaves more like a reluctant guardian of personal space than a predator searching for conflict. And then there are cobras, which evolved a completely different strategy altogether. In the dry grasslands and forests of Africa and Asia, some cobras developed one of the most unusual defensive systems in the animal kingdom: the ability to spit venom directly toward the eyes of predators. Certain species can project venom several feet with surprising accuracy, aiming not randomly, but specifically toward the face. Scientists believe this ability may have evolved partly in response to upright mammals and primates. A predator that relies heavily on vision becomes vulnerable if temporary blindness suddenly enters the equation. The cobra does not necessarily need to kill the threat. It only needs enough time to escape. And once again, survival appears more important than aggression. But cobras carry another layer of mystery beyond venom itself. Across human history, few snakes have embedded themselves into mythology as deeply. Ancient Egyptian rulers wore cobra imagery above their brows like divine protection. In India, cobras became intertwined with gods, creation myths, and spiritual symbolism. Something about the cobra's posture, rising upward, hood expanded, body perfectly still, creates an almost supernatural presence. It feels less like an animal and more like a warning from nature itself. Then there is the black mamba. Few snakes inspire fear quite like it. In movies and stories, the black mamba is often portrayed almost like pure death, moving through grasslands at impossible speed. And in some ways, reality does little to soften that image. Black mambas are among the fastest snakes on Earth, capable of moving far quicker than most people expect a snake should move. Their venom is primarily neurotoxic, attacking the nervous system with alarming efficiency. Before modern antivenom, untreated bites carried extremely high fatality rates. But even here, the popular image is not entirely accurate. Black mambas are not mindless attackers hunting humans across Africa. Many herpetologists describe them as highly alert, nervous animals that prefer escape whenever possible. However, when cornered, they become intensely defensive, lifting large portions of the body from the ground and striking repeatedly with terrifying speed. Perhaps that is what unsettles people most. Not simply the venom itself, but the speed at which events unfold once fear enters the encounter. A large predator gives visible signals. A charging bear announces danger loudly. But venomous snakes often operate in bursts of sudden silence so fast the human brain struggles to process what just happened. And nowhere does that silence feel stranger than beneath the ocean. Sea snakes remain some of the least understood venomous reptiles on Earth. Many species possess venom far more toxic drop for drop than their land relatives. Yet, divers sometimes swim near them without incident because sea snakes are often remarkably calm animals. Their venom evolved for a very specific purpose: Fish move quickly underwater, and injured prey can disappear into open ocean almost instantly. Sea snake venom became extraordinarily powerful because prey needed to stop moving immediately. Paralysis had to happen fast. Evolution turned efficiency into extremity. Some sea snakes even possess shorter fangs and relatively small mouths, creating the strange situation where highly venomous animals may struggle to bite large objects effectively at all. Again, reality becomes more complicated than fear alone suggests, and that complexity appears inside the venom itself. People often imagine venom as one substance, but snake venom is more like a shifting biochemical cocktail. Neurotoxins attack nerves. Hemotoxins damage blood and tissue. Cytotoxins destroy cells directly. Some snakes evolved combinations so intricate that scientists still study them protein by protein decades later. The Russell's viper, for example, carries venom capable of triggering catastrophic clotting problems inside the bloodstream. Victims may experience internal bleeding and kidney failure as the body's systems begin malfunctioning simultaneously. Meanwhile, snakes like the taipan focus more heavily on shutting down nerve communication itself. Different snakes evolved different answers to the same survival problem, and evolution never stopped experimenting. Some researchers suspect venom composition may continue changing, even within the same species, depending on geography, prey availability, or environmental pressure. A snake living in one region may produce venom chemically different from relatives living elsewhere. In a way, venom behaves almost like an evolving language between predator and prey, constantly adjusting over generations. That may explain why antivenom remains so difficult to produce. There is no universal antidote for all snake venom. Antivenoms are usually created by exposing animals, often horses or sheep, to carefully controlled venom doses, so antibodies can later be harvested and purified. But because venom chemistry varies so widely between species, treatment often requires precise identification. In remote parts of the world, that becomes a terrifying problem. A person may know they were bitten, but not by what. And time matters. In many rural regions across Africa, Asia, and South America, snakebite remains one of the most overlooked medical emergencies on Earth. The World Health Organization classifies snakebite envenoming as a neglected tropical disease, partly because the people most affected often live far from hospitals or antivenom supplies. For them, venom is not mythology. It is reality woven directly into everyday life. Farmers stepping through fields at dusk. Children walking barefoot near floodwaters. Villages built beside forests where humans and snakes have shared territory for centuries. The fear surrounding venomous snakes did not emerge from imagination alone. In many parts of the world, survival genuinely depended on learning which shadows to avoid. And perhaps that ancient fear still lingers somewhere inside the human nervous system. Some psychologists believe humans may possess unusually rapid visual sensitivity towards snake-like shapes and movement patterns. Certain studies suggest people detect snakes faster than many other threats, even in cluttered environments. Whether this response is fully evolutionary remains debated, but the reaction itself feels deeply ancient. A curved shape beneath leaves, a sudden movement beside a trail. The human brain notices before conscious thought fully catches up. Yet snakes themselves are far older than human fear. They survived asteroid impacts, ice ages, collapsing ecosystems, and millions of years of planetary change by becoming masters of efficiency. They do not waste limbs because they no longer need them. They do not waste energy chasing prey endlessly when chemistry can finish the task faster. Venom transformed snakes from physically vulnerable reptiles into some of evolution's most successful ambush predators. And still, most prefer retreat over conflict. That may be the final contradiction hidden beneath all the fear. The creatures humans often describe as evil are usually animals trying hardest to remain unseen. Hidden beneath rocks, buried under sand, motionless in branches above jungle trails. Venomous snakes did not evolve to hunt humanity. They evolved to survive a world where hesitation meant death. But evolution gave them something extraordinarily powerful along the way. A weapon carried not in claws or muscles, but in silence, moving invisibly beneath the skin after the bite is already over. Long before wolves learned to hunt in packs, before dinosaurs crossed ancient floodplains, before the first flower ever opened beneath sunlight, something with too many legs was already waiting in the dark. It hid beneath stone and bark in a world almost unrecognizable today. The air carried more oxygen than modern Earth. Forests looked alien. Giant insects drifted through humid swamps beneath towering prehistoric plants. And moving quietly across that ancient world were some of the oldest venom delivery systems evolution ever created. Spiders and scorpions survived nearly every major extinction event in Earth's history. That alone makes them strange. Entire dynasties of giant reptiles vanished. Oceans changed chemistry. Continents tore themselves apart. Temperatures rose and collapsed over millions of years. Yet somehow, these small, armored predators endured almost all of it, carrying the same basic hunting strategy across unimaginable stretches of time. Venom, not strength, not speed, not size, just precision. And perhaps that is why spiders and scorpions still feel deeply unsettling to humans even now. They move like creatures from another era because, in many ways, they are. Some scorpions alive today resemble ancient ancestors so closely that paleontologists sometimes describe them as evolutionary survivors rather than modern innovations. Hundreds of millions of years ago, giant sea scorpions, known as eurypterids, ruled prehistoric waters. Some reached lengths larger than humans. Whether all possessed venom remains uncertain, but they reveal something important about Earth's ancient ecosystems. The world before mammals was already filled with arthropod predators experimenting with armor, pincers, ambush tactics, and chemical weaponry. Modern scorpions inherited part of that ancient blueprint. And even now, beneath desert rocks or hidden inside dry canyon cracks, they still hunt, using methods that would feel familiar in prehistoric darkness. A scorpion does not chase prey for long distances. It waits, motionless. Sensitive hairs along its body detect tiny vibrations moving through sand. A passing insect may not even realize danger exists until pincers close around it and the stinger arches forward overhead like a living needle. Then chemistry enters the body. Some scorpion venom primarily causes pain so intense it feels electrically unnatural. Others interfere with nerve signaling itself, creating muscle spasms, breathing difficulties, or paralysis. The deathstalker scorpion of North Africa and the Middle East became infamous partly because its venom combines terrifying potency with a body small enough to disappear almost anywhere, which creates one of nature's strangest contrasts. The smaller the creature, the more carefully humans tend to watch it. A lion announces danger loudly. A crocodile creates ripples in water. But a venomous scorpion can hide beneath a shoe, inside wood piles, beneath blankets, or in cracks no wider than a finger. Fear becomes psychological because the threat feels invisible long before it becomes physical. And scorpions carry another secret most people never notice. Under ultraviolet light, many species glow an eerie blue-green color. Scientists still debate exactly why. Some researchers suspect the fluorescence may help detect moonlight levels. Others believe it could be an accidental byproduct trapped inside the exoskeleton over evolutionary time. No explanation has achieved universal agreement, but the image itself feels almost supernatural. Ancient venomous predators glowing silently beneath desert darkness as though carrying remnants of prehistoric chemistry inside their armor. Then there are spiders. If scorpions feel ancient, spiders feel alien. Not because they are aggressive, but because they evolved into some of the most efficient ambush predators Earth has ever produced. A spider's web alone represents astonishing biological engineering. Silk stronger than steel by weight. Vibrational sensitivity precise enough to distinguish wind from prey movement. Venom calibrated not merely to kill, but often to liquefy internal tissue. That last detail unsettles many people once they truly understand it. Most spiders cannot consume solid food the way mammals do. Their venom often begins digesting prey internally before feeding even starts. The spider is not simply killing, it is transforming another body into something drinkable. And evolution refined this process with terrifying efficiency. The black widow became one of the most infamous examples in North America. Its venom attacks the nervous system, triggering waves of pain, muscle cramping, and severe discomfort. Yet, despite its reputation, black widows are remarkably shy creatures. Bites usually happen when humans accidentally trap or press against them. Again, the pattern repeats. The most feared venomous creatures are often the ones trying hardest to avoid conflict. But spiders frighten humans differently than snakes. A snake, at least, feels emotionally understandable. It has eyes that follow movement, muscles that resemble larger animals, a visible head and mouth. Spiders trigger something stranger. Too many legs, sudden movement without sound, bodies that seem almost mechanical, instead of emotional. Some psychologists believe spider fear may partially connect to unpredictability. Human brains struggle to read spiders the way they read mammals. We cannot easily interpret intention in a creature that pauses motionless for minutes and then moves with startling speed across walls or ceilings. That uncertainty amplifies fear, and nature gave spiders countless ways to deepen it. Trapdoor spiders build hidden underground tunnels, sealed almost invisibly with silk-covered doors. Orb weavers construct enormous geometric webs capable of catching prey far larger than themselves. Jumping spiders hunt with startling intelligence and visual precision. Tarantulas, despite their terrifying appearance, often rely more on intimidation than deadly venom. In fact, many tarantulas are less dangerous to humans than popular culture suggests. Their real weapon is psychological. Large bodies, thick legs, slow, deliberate movement. The image alone triggers instinctive discomfort long before venom enters the conversation. Some species even defend themselves using clouds of irritating hairs kicked from the abdomen into the air. Nature discovered that fear itself could become survival armor. Yet among all spiders, few feel more disturbing than the Sydney funnel-web spider of Australia. Unlike many shy species, funnel webs may behave more aggressively when threatened. Their venom can attack the nervous system rapidly enough that untreated bites were once frequently fatal before effective antivenom became available. And male funnel webs appear significantly more dangerous than females. Scientists believe males wander more frequently while searching for mates, increasing encounters with predators and possibly shaping venom potency differently over time. Even inside venom systems, evolution continues adjusting behavior, chemistry, and survival strategy simultaneously. The deeper researchers study venomous arthropods, the stranger the story becomes. Some toxins are unbelievably specific. Certain spider venoms target ion channels inside nerve cells with molecular precision. Others attack insects far more effectively than mammals because the spider evolved primarily to hunt arthropods, not large animals. Humans are often accidental participants in systems never designed around us. That realization changes the emotional atmosphere completely. Venomous spiders and scorpions are not ancient monsters waiting for human victims. Most evolved for tiny wars happening beneath leaves, stones, bark, and desert sand long before human beings arrived. Entire invisible ecosystems exist at our feet constantly. A web trembling beneath moonlight, a scorpion sensing footsteps through sand grains, a spider waiting motionless beside a tunnel entrance for hours without moving. Predators operating in silence at scales humans rarely notice. And perhaps the most fascinating part is how successful the strategy became. Spiders now exist on nearly every continent except Antarctica. Scorpions survive in deserts, forests, mountains, and caves across the world. They endured because venom allowed them to remain small while still controlling prey efficiently. They did not need to evolve massive bodies or overwhelming strength. Chemistry solved the problem more elegantly. In some ways, these creatures became masters of energy conservation. Minimal movement, minimal wasted effort, precise attacks. Evolution often rewards efficiency more than power, and spiders may represent one of the clearest examples of that principle anywhere in nature. But there is another layer to this story that humans only recently began understanding. Venom may also contain medicine. Researchers now study compounds from spider and scorpion venom for potential use in pain treatment, neurological disorders, and even cancer research. Certain molecules interact with nerve pathways so precisely that scientists believe they may help target diseased cells or chronic pain in ways conventional drugs struggle to achieve. Once again, nature reveals the same contradiction hidden throughout the venomous world. The substances capable of causing suffering may also carry healing potential. And perhaps that contradiction explains why humans remain so fascinated by these creatures despite fear. Spiders and scorpions feel ancient not only because they survived prehistoric Earth, but because they expose something deeper about evolution itself. Nature is not sentimental. It does not create beauty separately from danger. The same delicate spiderweb shining with morning dew also functions as a lethal trap. The same glowing scorpion hidden beneath ultraviolet light carries chemistry capable of overwhelming a nervous system. Evolution blends elegance and violence together so completely that separating them becomes impossible. And somewhere tonight, beneath a rock still warm from the desert sun, or inside the dark corner of an old wooden shed, another ancient predator waits motionless in silence, armed with a weapon older than humanity itself. Far below the surface of the ocean, where sunlight begins fading into deep blue darkness, something almost invisible drifts through the water like a floating piece of glass. There are no teeth, no claws, no sound at all. Just long, translucent tentacles moving slowly beneath the current. And yet, inside those tentacles are millions of microscopic weapons waiting for contact. The box jellyfish does not hunt the way humans usually imagine predators hunting. It does not chase prey across reefs or tear flesh apart with visible force. Instead, it carries one of the most sophisticated venom delivery systems ever created by evolution. Tiny harpoon-like cells called nematocysts explode outward when touched, injecting venom with astonishing speed. Some scientists estimate the discharge happens in microseconds, faster than many mechanical systems humans have ever built. And the venom itself is terrifying. Box jellyfish toxins can attack the heart, nervous system, and skin simultaneously. In severe cases, victims may experience overwhelming pain, cardiac collapse, or paralysis within minutes. Yet what makes the animal feel truly unnatural is its appearance. It looks delicate, almost harmless, transparent enough to disappear inside shallow tropical water. That contrast may explain why the ocean produces a different kind of fear than land. On land, danger usually announces itself. A growl in the dark, heavy footsteps, sharp teeth. But underwater, evolution often moves toward invisibility instead. Camouflage, silence, transparency. Venom hidden inside creatures that barely appear alive at all. And nowhere does that evolutionary strategy become stranger than among venomous marine animals. The blue-ringed octopus, small enough to fit in the palm of a hand, carries venom powerful enough to stop human breathing entirely. At first glance, it hardly looks threatening. Its movements are slow and almost curious, drifting between coral and rocks like a tiny, intelligent shadow. But when disturbed, electric blue rings suddenly begin glowing across its skin. It is one of the clearest warning signals in nature. Hidden inside the octopus is tetrodotoxin, a neurotoxin so potent that even tiny amounts can interfere with the nervous system catastrophically. Victims may remain conscious while losing the ability to move or breathe. And perhaps the most unsettling part is that there is no true antivenom, only support, oxygen, time. The ocean is filled with creatures like this, animals carrying chemistry so powerful that modern medicine still struggles to fully counter it. And many of them do not even look like predators. The stonefish may be the perfect example. Resting motionless along the sea floor, it resembles nothing more than a piece of coral-covered rock. Algae and rough textures break apart its outline until it almost disappears into the reef completely. Then a foot touches it. Venomous spines along the fish's back drive upward instantly, injecting toxins capable of causing agony so severe that survivors sometimes describe the pain as psychologically overwhelming. Yet, even here, the stonefish is not truly aggressive. It does not chase swimmers. It does not hunt humans. It survives through invisibility. That may be one of the deepest patterns hidden beneath marine venom systems. In the ocean, remaining unseen is often more important than appearing powerful. Open water leaves creatures exposed from every direction. Venom became a way for slow or vulnerable animals to survive without constant movement or combat. And some species evolved delivery systems so bizarre they almost feel alien. The cone snail glides slowly across coral reefs, carrying what looks like an elegant seashell no larger than a golf ball. Divers sometimes pick them up without realizing they are touching one of the most sophisticated venom hunters in the ocean. Inside the snail is a biological harpoon. When prey approaches, the snail fires a sharp, venom-loaded tooth forward with startling speed. The toxins move through fish nervous systems almost instantly, causing paralysis before escape becomes possible. Some cone snail venoms contain hundreds of different compounds working together simultaneously, forming one of the most chemically complex weapons found anywhere in nature. Researchers still study them molecule by molecule. And perhaps the strangest part is that many marine venoms appear far more precise than land-based toxins. Certain compounds target extremely specific nerve pathways with remarkable efficiency. Evolution inside the ocean may have pushed venom chemistry toward extraordinary specialization because underwater prey can vanish so quickly if not stopped immediately. Fish do not collapse onto the ground after injury. They disappear into endless water, which means hesitation becomes failure. That pressure may explain why some of the world's most potent venoms evolved beneath the sea. Sea snakes, for example, possess venom that can be dramatically more toxic, drop for drop, than many terrestrial snakes. Yet, they are often calm animals, drifting through coral reefs with graceful movements that feel almost peaceful. Their venom evolved not from aggression, but from necessity. Fish prey needed to stop moving immediately before escaping into open ocean currents. Again, efficiency became extremity, and sometimes the ocean pushed venom evolution into directions so strange that scientists still debate how certain systems even developed in the first place. The Portuguese man-o-war, often mistaken for a jellyfish, is not technically a single animal at all. It is a floating colonial organism made from multiple specialized living parts working together. Tentacles stretching dozens of feet beneath the water carry stinging cells capable of inflicting intense pain and, in rare cases, serious medical emergencies. An entire floating colony behaving like one creature. The deeper humans explore marine biology, the more the ocean begins feeling less like an ecosystem and more like another world entirely. Even tiny creatures drifting in darkness may carry chemistry capable of overwhelming much larger animals. Some toxins attack nerves, others disrupt muscles or heart rhythms. A few create pain so intense that victims become disoriented before understanding what touched them. And unlike on land, the ocean often hides the source completely. A swimmer may never see the tentacle beneath the surface. A diver may brush against venomous coral accidentally. A fisherman may step on a hidden stonefish buried beneath sand. The attack feels invisible because, in many cases, it practically is. Perhaps that is why marine venom carries such psychological weight. Humans evolved primarily on land. We understand forests, plains, mountains, and storms instinctively. But beneath the ocean's surface, normal survival logic begins breaking apart. Visibility changes. Sound behaves differently. Movement slows. And hidden within that unfamiliar environment are venom systems older than humanity itself. Some researchers believe marine venom compounds may eventually transform medicine as well. Certain cone snail toxins are already being studied for pain treatment because they target nerve pathways with astonishing precision. Scientists continue examining jellyfish, sea anemones, and venomous fish for compounds that may help treat neurological disorders or cardiovascular disease. Once again, nature reveals the same contradiction hidden throughout the venomous world. The chemistry capable of causing suffering may also contain healing. And perhaps nowhere is that contradiction stranger than in coral reefs themselves. Reefs appear beautiful from above. Bright fish, clear water, sunlight shimmering across living stone. But beneath that beauty exists constant chemical warfare. Tiny animals defend territory using toxins. Predators immobilize prey chemically. Survival unfolds through invisible biological interactions happening every second across the reef. The ocean does not separate elegance from danger. It combines them. A glowing octopus carrying fatal venom. A transparent jellyfish drifting like glass. A motionless fish disguised as stone itself. a beautiful shell concealing a biological harpoon. The deeper evolution moved beneath the sea, the more it seemed to favor deception over intimidation. And perhaps that makes sense. In darkness, silence becomes power. Some marine scientists suspect humans have explored only a small fraction of ocean biodiversity, especially in deep environments where sunlight never reaches. Entire venom systems may exist undiscovered beneath abyssal depths. Strange organisms continue appearing during deep-sea expeditions, with anatomy so unfamiliar that researchers sometimes struggle to classify them immediately. It is entirely possible the ocean still hides venom compounds more powerful or biologically unusual than anything humans currently know. That idea becomes even more unsettling when you remember how little of the deep ocean has truly been explored. More humans have walked on the moon than visited the deepest parts of Earth's oceans. Vast regions remain cold, dark, and almost completely beyond direct human observation. Somewhere down there, evolution has been experimenting uninterrupted for hundreds of millions of years. And unlike humans, the ocean never needed fire, machines, or language to create weapons more chemically advanced than many laboratories on Earth. It only needed time. Tonight, beneath black water deeper than mountains are tall, venomous creatures continue drifting silently through darkness older than civilization itself. No roar reaches the surface, no warning echoes upward, just invisible chemistry waiting patiently in the cold. Inside animals that often look more like ghosts than predators. At first, the body often does not understand what has happened. A person walking through tall grass may feel nothing more than a sharp sting near the ankle. A diver brushing against drifting tentacles may initially mistake the sensation for simple irritation. Sometimes there is barely any pain at all in the first few seconds. The skin may look almost normal. And yet, beneath the surface, millions of molecules have already entered the bloodstream. That may be the most unsettling thing about venom. The real attack often begins invisibly. Long before humans understood nerves, blood chemistry, or electrical signals inside the body, venom was already exploiting them with astonishing precision. Evolution spent hundreds of millions of years refining toxins capable of interrupting life at its most delicate biological points. Not through brute force, not by tearing the body apart directly, but by convincing the body to malfunction itself. And once that process begins, the human body can become strangely unfamiliar even to the person trapped inside it. Some venoms attack the nervous system first. Neurotoxins move through the body, searching for communication pathways between nerves and muscles. Under normal conditions, your brain constantly sends electrical instructions through the nervous system without conscious effort. Breathe, blink, swallow, keep the heart beating, move the diaphragm again, maintain rhythm. You never notice these commands happening because they are automatic. Venom changes that. Certain neurotoxins interfere with the tiny chemical exchanges allowing nerves to communicate with muscles. Signals begin weakening or stopping entirely. Eyelids feel heavy. speech becomes difficult. Muscles stop responding correctly. Eventually, the diaphragm itself, the muscle responsible for breathing, may fail to move. The terrifying part is that consciousness can remain intact during this process. Some victims of severe neurotoxic envenomation have described feeling mentally awake while the body slowly stopped obeying them. The lungs do not forget how to exist. They forget how to move. And evolution discovered this strategy because it works incredibly fast against prey. A fish drifting paralyzed through water cannot escape. A rodent unable to breathe becomes defenseless within minutes. Venom evolved not around cruelty, but efficiency. The quicker prey stops moving, the less energy a predator wastes. But not all venom attacks nerves. Some species evolved something equally horrifying in an entirely different direction. Hemotoxic venom targets blood and tissue instead. Rather than shutting down communication, these toxins begin disrupting the body's internal structure itself. Blood vessels weaken, clotting mechanisms malfunction, cells break apart. Tissue surrounding the bite may swell, darken, or begin dying as circulation collapses. In some cases, the body almost seems to turn against itself. Certain snake venoms create catastrophic clotting throughout the bloodstream, using up clotting factors until uncontrolled bleeding later begins elsewhere in the body. Others destroy red blood cells directly or damage kidneys attempting to filter the biochemical chaos moving through circulation. To ancient humans, these effects must have looked supernatural. A person could appear healthy after the bite, then gradually deteriorate over hours as invisible chemistry spread internally beneath the skin. Without understanding biology, venom would have seemed less like injury and more like a curse unfolding from within. And perhaps the most disturbing detail is how differently human bodies respond. Two people bitten by the same species may experience dramatically different outcomes. Body size matters. Venom dosage matters. Bite location matters. Age, health, stress response, even how quickly the body distributes toxins through circulation, all can influence survival. Sometimes, fear itself becomes part of the event. Adrenaline floods the bloodstream almost immediately after envenomation. The heart beats faster. Circulation changes. Breathing accelerates. In certain situations, that stress response may actually move venom through the body more quickly. Yet, adrenaline can also temporarily help maintain blood pressure or alertness during trauma. The body is trying to save itself while simultaneously helping toxins travel. That contradiction reveals something profound about venom. It evolved specifically against living systems already designed for survival. Venom does not merely overpower biology, it manipulates biology's own rules. Some toxins even attack pain itself. The bullet ant of Central and South America delivers one of the most painful stings known in nature. Victims often describe waves of agony that feel electrically unnatural, as though the nervous system itself is malfunctioning. Certain marine venoms create pain so overwhelming that people become disoriented before visible physical damage fully appears. Why evolve extreme pain at all? In many cases, pain functions as defense rather than predation. A predator only needs one unforgettable encounter to avoid attacking the same species again. Evolution discovered that agony can be protective, and the body responds to pain in fascinating ways. Under extreme stress, perception itself sometimes changes. Time may feel distorted. Memory becomes fragmented. Victims occasionally struggle to describe sensations accurately afterward because the nervous system enters survival mode. The experience becomes not only physical, but psychological. Venom attacks the mind indirectly through the body. And some toxins go even further. Tetrodotoxin, carried by creatures like the blue-ringed octopus and certain pufferfish, blocks sodium channels essential for nerve signaling. Muscles gradually stop responding, while awareness may remain frighteningly clear. Historically, toxins like these likely contributed to myths about curses, paralysis, or states resembling death itself. There are even historical accounts of people appearing almost lifeless after exposure to certain toxins before later recovering. Stories that may have fueled folklore long before chemistry explained what was truly happening. But evolution did not design venom specifically for humans. That may be the most important thing to remember. Venom evolved for prey animals far smaller than us. A spider evolved to subdue insects. A sea snake evolved to stop fish from escaping. Humans are often accidental participants in systems never intended around our biology at all. And yet, some venoms interact with the human body with terrifying effectiveness because the fundamental architecture of life is shared across species. Nerves operate similarly. Muscles communicate similarly. Blood carries oxygen similarly. Evolution discovered universal vulnerabilities hidden inside complex organisms long before humans understood them scientifically. The deeper researchers study venom, the more precise it appears. Some toxins target specific receptor sites, almost like molecular keys fitting into biological locks. Others combine dozens or even hundreds of compounds working together simultaneously. Certain snake venoms contain enzymes, neurotoxins, anticoagulants, and tissue-damaging compounds, all mixed into one evolving biochemical system. It is less like a single poison and more like coordinated biological software written through evolution. And perhaps nowhere does this become stranger than in the body's immune response. The immune system reacts immediately to venom, but not always effectively. Swelling, inflammation, fever, nausea, and shock may follow as the body struggles to interpret what is happening. In severe allergic reactions, the immune system itself becomes dangerous, triggering anaphylaxis, capable of threatening life independently from the venom. Sometimes the body panics almost as violently as the toxin itself. Yet humans also possess remarkable resilience. Many venomous bites are survived without lasting damage. Medical treatment improved dramatically over the last century. Antivenoms save thousands of lives every year. Intensive care can support breathing, while neurotoxins slowly leave the body. Fluids, oxygen, and modern monitoring transformed survival rates for many species once considered nearly untreatable. Still, venom retains something deeply mysterious, even inside modern hospitals. Doctors may know roughly what a toxin does, while still struggling to predict exactly how one individual body will respond. Venom interacts with metabolism, circulation, immune response, genetics, and stress in extraordinarily complex ways. No two envenomations unfold identically, and evolution continues changing the chemistry itself. Some researchers suspect venom composition may shift over time depending on prey availability, environment, or evolutionary pressure. Even within the same species, regional differences in venom chemistry can occur. Nature is still experimenting with these molecules right now across forests, deserts, reefs, and oceans worldwide, which means humanity may not fully understand the limits of venom yet. And strangely, inside all this danger, scientists also discovered possibility. Certain venom compounds are now studied for pain management, blood pressure treatment, stroke research, and neurological disease. Molecules evolved to interrupt biological systems may eventually help repair them under controlled medical conditions. Again, nature refuses simple categories. The same chemistry capable of shutting down lungs may also help save future patients in hospitals. The same toxins, once feared as symbols of death, may eventually become medicine. Perhaps that contradiction exists because venom reveals something uncomfortable about life itself. Human bodies feel solid and permanent from the inside. We trust our heartbeat, our breathing, our movement. But venom exposes how fragile those systems truly are. Tiny molecules, measured in microscopic amounts, can interrupt processes we rely on every second without thinking. Breathing is chemistry. Thought is chemistry. Movement is chemistry. And evolution learned how to reach into those systems long before humanity ever realized they existed. Tonight, somewhere beneath jungle leaves, desert sand, or drifting ocean currents, venom is still moving silently through living bodies, exactly as it has for millions of years. Invisible, efficient, and disturbingly precise. Reminding every creature on Earth that survival has always depended on the smallest hidden reactions happening deep beneath the skin. Deep in the rivers of eastern Australia, a small animal slips silently through dark water beneath overhanging branches. At first glance, it hardly seems real. It has the bill of a duck, the tail of a beaver, the fur of an otter, and feet that look borrowed from several different creatures at once. For a long time, European scientists genuinely believed the platypus was a hoax. Some thought somebody had stitched multiple animals together. And perhaps the strangest part is that even now, centuries later, scientists still do not fully understand everything hidden inside it. Because the male platypus carries venom. Near the hind legs are sharp spurs connected to venom glands capable of delivering one of the most painful mammalian venoms known. Human victims rarely die from it, but many describe the pain as almost psychologically overwhelming, resistant to morphine, and capable of lingering for weeks or even months. Which raises an unsettling question. why would a semi-aquatic mammal evolve venom at all? Venom appears commonly in snakes, spiders, jellyfish, and scorpions, but mammals rarely use it. The platypus seems to exist in a strange biological gray zone, almost like a surviving fragment from an alternate evolutionary timeline where mammals experimented with stranger survival strategies than the ones dominating Earth today. And that may be exactly what happened. The platypus belongs to one of the oldest mammalian lineages still alive. It lays eggs instead of giving birth to live young. It detects electrical signals underwater, and its venom appears connected more to territorial competition between males than hunting prey. Evolution built something so unusual that even modern biology still struggles to categorize parts of it comfortably. Then there is the slow loris. High in the forests of Southeast Asia, one of the few venomous primates on Earth moves through branches with enormous reflective eyes glowing softly in darkness. At first glance, it looks almost impossibly harmless. Small hands gripping branches slowly, movements gentle and deliberate, like a living, stuffed animal. But hidden near its elbows are glands producing toxic secretions. When threatened, the slow loris licks these glands and mixes the chemicals with saliva before biting. Scientists are still debating exactly how its venom evolved and how dangerous it truly is across different situations. But reactions in humans can be severe, including tissue damage and potentially life-threatening allergic responses. The deeper researchers study venom, the stranger the evolutionary story becomes. Because venom keeps appearing in places where humans never expected it. Even birds may not be completely excluded from this hidden world of toxins. The hooded pitohui of New Guinea carries powerful neurotoxins within its skin and feathers, likely obtained through diet rather than producing the toxins internally. Some scientists believe the bird essentially turns itself poisonous by consuming toxic beetles and incorporating the chemistry into its own body. A bird becoming toxic through what it eats sounds almost fictional. Yet nature repeatedly creates systems more bizarre than mythology. And perhaps nowhere is that more obvious than among poison dart frogs. Bright blue, yellow, orange, red. They look less like animals and more like warning signs painted by evolution itself. Tiny poison dart frogs in Central and South America carry toxins potent enough to kill predators far larger than themselves. Indigenous communities historically used some species to poison blow darts for hunting, giving the frogs their famous name. Yet, what makes them truly fascinating is where the toxins may actually come from. Many researchers believe poison dart frogs do not fully manufacture their deadliest chemicals alone. Instead, the toxins may originate from ants, mites, and other tiny prey consumed in the wild. Captive frogs raised on different diets often become dramatically less toxic over time, which means the forest itself may partly create the poison. That idea changes the way venom and toxicity feel entirely. The animal is no longer simply a weapon. It becomes part of a larger chemical network flowing through the ecosystem. and ecosystems can produce combinations stranger than almost anything humans intentionally design. Consider the Komodo dragon. For decades, scientists debated how exactly these giant reptiles killed prey so efficiently. Older theories suggested bacteria in the dragon's saliva caused fatal infections after bites. But more recent research revealed venom glands containing anticoagulant and shock-inducing compounds that may contribute significantly during attacks. Yet debate still continues. Some researchers argue venom plays a central role. Others believe physical trauma and blood loss remain more important. The truth may involve multiple systems working together simultaneously. That uncertainty matters because it reveals how much scientists still do not fully understand, even in large, famous predators humans have studied for generations. And sometimes the mystery becomes even deeper when researchers begin examining creatures living far below human observation. In the deepest regions of the ocean, bizarre fish and invertebrates drift through darkness under crushing pressure where sunlight never reaches. Some carry venom systems so unfamiliar that scientists struggle to compare them cleanly with terrestrial animals at all. The vampire squid, despite its dramatic name, is not truly venomous as far as current evidence shows, yet its appearance alone, glowing eyes, dark webbed arms, bioluminescent displays, demonstrates how alien deep ocean evolution can become when isolated from surface ecosystems for millions of years. It raises an uncomfortable possibility. If shallow oceans already contain creatures like cone snails and blue-ringed octopuses, what kinds of venom systems might still exist undiscovered in abyssal depths humans barely explore? That question becomes even stranger when researchers examine how flexible venom itself can be. Some species appear capable of adjusting venom composition depending on geography, prey type, season, or even age. Juvenile snakes may produce chemically different venom than adults because they hunt different prey. Certain spiders alter toxin expression based on environmental conditions. Venom is not always static. It evolves continuously, and perhaps evolution is still experimenting in ways humans have barely noticed. Some scientists suspect many animals possess mild or primitive venom systems hidden in plain sight. There are debates involving shrews, certain lizards, and other species carrying saliva or glandular secretions that blur the line between ordinary biology and true venom delivery. The boundary itself may be artificial. Humans like categories: venomous, poisonous, harmless, dangerous. Nature rarely cares about those distinctions. Instead, evolution modifies existing systems gradually across immense stretches of time until something entirely new appears. A digestive enzyme becomes irritating. An irritating compound becomes defensive. A defensive secretion becomes specialized venom. And suddenly, a tiny mammal in a rainforest or an ancient reptile on an island possesses chemistry humans never expected. Perhaps the most unsettling realization is how often scientists discover useful medical potential hidden inside these bizarre toxins. Certain venom compounds target nerve pathways with extraordinary precision. Others affect blood pressure, clotting, or pain signaling in ways pharmaceutical researchers study intensely. What once appeared only terrifying may eventually become medically valuable. Again and again, nature reveals the same contradiction. The line between poison and medicine depends heavily on dosage, context, and understanding. Some of the world's strangest animals may eventually help humans treat disease, precisely because evolution spent millions of years refining biochemical systems no laboratory could easily invent from scratch. And still, much remains unknown. Researchers continue discovering new venom peptides and toxins every year. Rainforests, coral reefs, caves, deserts, and deep oceans still contain organisms barely studied at all. Entire branches of venom evolution may remain undocumented simply because humans have not encountered them yet. That possibility changes the emotional atmosphere surrounding the natural world. Venom is no longer just a weapon carried by familiar predators. It becomes evidence that evolution itself is far stranger than human imagination tends to assume. A duck-billed mammal carrying venomous spurs. A primate with toxic saliva. A bird infused with poison through diet. Tiny frogs glowing with chemical defense. Ancient reptiles still confusing modern science. The deeper humans investigate biology, the less predictable life becomes. And perhaps that unpredictability is the real reason these creatures fascinate us so deeply. They remind us that Earth is not fully understood, even now. Beneath rainforest canopies, inside dark rivers, under coral reefs, and deep within unexplored oceans, evolution continues, running experiments in silence, exactly as it always has. Some of those experiments survived millions of years. Some may still be changing. And somewhere tonight, hidden far from human cities, beneath jungle leaves or black water, another strange creature carries chemistry so unusual that science may not fully understand it for decades to come, if humanity discovers it at all. Long before humans understood chemistry, they already feared it. Not in laboratories, not in medicine bottles, but in roots buried beneath soil, strange powders mixed into wine, and venom hidden silently inside fangs waiting in the dark. Somewhere, thousands of years ago, beside firelight flickering against cave walls, a human being likely watched another collapse after eating the wrong plant or suffering the wrong bite. There were no microscopes, no toxicology reports, no understanding of proteins or neurotoxins moving through blood. Only mystery. And perhaps that is where humanity's obsession with poison truly began. Because poison feels different from ordinary violence. A spear can be seen. A predator can be heard approaching through the forest. But poison operates invisibly, quietly. It enters the body without announcing itself, transforming food, drink, medicine, or even touch into something dangerous. It turns trust itself into uncertainty. That psychological terror shaped human civilization far more deeply than most people realize. Ancient rulers feared poisoning so intensely that some employed official food tasters whose sole purpose was to risk death first. Across royal courts, empires, and kingdoms, poison became associated with betrayal because it bypassed physical strength entirely. A weak person could kill a king without armies. A servant could destroy a dynasty with a single cup. And unlike open violence, poison often left confusion behind. The victim became sick gradually. Symptoms resembled disease. Weakness emerged invisibly. Before modern medicine, distinguishing murder from illness could be nearly impossible. That uncertainty gave poison enormous psychological power throughout history. Even mythology absorbed it. In ancient Greece, the hydra's venom was said to be so deadly that arrows dipped into it caused nearly unstoppable suffering. In Egypt, snakes became symbols of both divine protection and death at the same time. In India, venomous cobras entered spiritual traditions as creatures representing danger, rebirth, and hidden power simultaneously. Again and again, poison occupied a strange place in the human imagination. Not simply evil, not simply magical, but something existing between nature and the supernatural. And perhaps no historical figure embodies that mystery more than Cleopatra. For centuries, stories claimed the Egyptian queen died from the bite of an asp, likely some form of cobra. Yet, historians still debate whether that account is fully accurate. Some researchers argue poison mixtures may have been more practical or reliable than a live snake. Others believe the symbolic power of the serpent itself became too irresistible for ancient storytellers to ignore, because snakes carried meaning beyond biology. A ruler dying by venom felt mythic. Even today, the image survives because poison creates narratives humans cannot stop retelling. Assassins, secret potions, kings collapsing during feasts, ancient cups lined with hidden toxins. Entire civilizations developed paranoia around invisible death moving silently through trusted spaces. And much of that fear came from one terrifying realization. You do not need physical dominance to use poison. That changed warfare too. Some indigenous hunting cultures coated arrows or blow darts with toxins extracted from frogs, plants, or venomous animals. The goal was not spectacle, it was efficiency. A small wound became deadly because chemistry continued the attack after impact. Nature provided the weapon. Humans adapted it. And over time, civilizations began studying toxins with unsettling fascination. Ancient physicians sometimes worked dangerously close to poison makers themselves. The difference between medicine and toxin often depended almost entirely on dosage. Small amounts of certain compounds relieved pain or illness. Slightly larger amounts caused death. That boundary remains disturbingly thin even now. In fact, many substances humans consider medicinal today would become dangerous under different conditions. Poison and medicine are not opposites as much as they are neighboring territories separated by precision. Perhaps that is why humanity became obsessed with understanding toxins instead of simply fearing them. But fear never disappeared completely. Some psychologists believe humans may possess unusually rapid sensitivity towards snakes and spiders because venomous animals threatened early primates for millions of years. Certain studies suggest people detect snake-like shapes faster than many other visual patterns, even when partially hidden. Whether those responses are fully inherited remains debated. But the emotional reaction itself feels ancient. A curved shape beneath leaves. A sudden movement near the footpath. A spider crossing a wall late at night. The body reacts before logic fully arrives. And poison became even more frightening precisely because it could not always be seen at all. In medieval Europe, fear of poisoning reached extraordinary levels. Nobles worried about tainted wine, poisoned bread, contaminated rings, cosmetics, perfumes, and medicines. Political rivals accused one another constantly. Some rumors became wildly exaggerated, but that only strengthened the atmosphere of paranoia surrounding toxins. Invisible death creates imagination faster than visible violence ever could. You can defend yourself against a sword. How do you defend yourself against uncertainty? That question may explain why poison became associated so closely with conspiracy, secrecy, and hidden intentions across human history. Assassination by blade feels direct. Poison feels personal, intimate, quiet. The victim often never sees the attack begin. And yet, humanity's relationship with poison was never entirely fearful. Sometimes it became admiration. Mithridates VI, an ancient king of Pontus, supposedly feared assassination so intensely that he regularly consumed tiny amounts of poison in an attempt to build immunity. Whether all stories surrounding him are accurate remains uncertain, but the concept became famous enough to inspire the term Mithridatism. Resistance developed through gradual exposure. The idea itself sounds almost mythological. A human intentionally training against poison, like preparation for invisible war. And strangely, there is some scientific logic behind parts of it. Controlled exposure can produce limited tolerance in certain circumstances. Modern antivenom production relies partly on carefully exposing animals to venom so antibodies develop over time. Again, humanity did not merely fear toxins. It tried to master them. That fascination continued into modern science, where researchers began isolating compounds from venomous animals not only to understand death, but to understand life itself. Neurotoxins revealed how nerves communicate. Venoms exposed hidden mechanisms inside blood clotting, muscle control, and cellular signaling. Poison became a map of human biology. The very substances once feared as supernatural curses eventually helped scientists understand how the body functions at its deepest levels. And perhaps that transformation reveals something important about human nature. We are drawn toward danger intellectually, even while fearing it emotionally. People watch venomous snakes behind glass, read murder mysteries involving poison, study toxic plants, explore abandoned chemical disasters. Something about invisible danger captures human curiosity differently than ordinary violence, because it forces the imagination to participate. You cannot always see poison working. You picture it instead, and imagination often becomes more frightening than reality itself. Yet reality remains strange enough already. Certain poisons disrupt oxygen use inside cells so effectively that the body essentially begins suffocating despite air still entering the lungs. Others attack nerves, memory, muscles, or heart rhythms. Some plants evolved toxins specifically to discourage herbivores long before humans existed, creating chemical defenses hidden inside forests and fields worldwide. The earth itself became filled with invisible biological warfare long before humanity appeared. Humans simply entered an already toxic world, and perhaps that is why poison still feels deeply symbolic today. It represents more than physical danger. It represents hidden consequences, uncertainty, betrayal, the unsettling truth that something small and unseen can overpower something large and strong. Entire empires feared that idea. Entire religions transformed it into metaphor. Even language absorbed it. Toxic relationships, poisoned minds, venomous words. Humans instinctively use poison to describe invisible harm moving beneath the surface because the emotional logic feels immediately understandable. Poison destroys quietly, sometimes slowly enough that fear grows alongside it. And despite all modern science, traces of ancient superstition still remain. People continue sharing myths about cursed toxins, deadly creatures, mysterious assassinations, and impossible survivals, because poison exists at the intersection of biology and imagination more than almost any other natural force. It attacks from inside the body, a place humans cannot directly observe. That alone makes it psychologically powerful. Tonight, somewhere in the world, venom still drips from fangs beneath jungle leaves. Toxic frogs still glow softly in rainforest darkness. Plants still manufacture chemicals designed to discourage anything that tries to consume them. And humans continue watching all of it with the same mixture of fear and fascination our ancestors felt beside ancient fires thousands of years ago. Still haunted by the possibility that the deadliest things in nature are often the ones we cannot see moving through us at all. Inside a brightly lit laboratory, a scientist carefully lowers a tiny droplet of venom into a glass container no larger than a fingertip. The liquid itself looks almost harmless, clear, quiet, ordinary. And yet somewhere inside that drop may exist molecules capable of stopping a heart or saving one. That contradiction has become one of the strangest discoveries in modern science. For most of human history, venom represented fear, something hidden in fangs, tails, tentacles, or stingers, waiting beneath rocks and dark water. But over the last century, researchers began realizing something deeply unsettling and unexpectedly hopeful at the same time. Venom works because it is precise. Evolution spent hundreds of millions of years refining toxins capable of interacting with nerves, blood vessels, muscles, and organs more accurately than many human-designed chemicals ever could. A snake does not need venom to destroy an entire body indiscriminately. It only needs to interrupt the right system at the right moment. And modern medicine became fascinated by that precision, because disease is often a problem of systems malfunctioning inside the body. Blood pressure rises too high, pain signals refuse to stop. Cells divide uncontrollably. Nerves misfire. Muscles weaken. Somewhere deep inside biology, communication begins failing. Venom already knows how to reach into those systems. That realization changed everything. One of the earliest major breakthroughs came from the venom of a Brazilian pit viper. Scientists studying the snake noticed compounds affecting blood pressure in remarkable ways. Over time, this research contributed to the development of ACE inhibitor medications, drugs that would eventually help millions of people manage hypertension and heart disease worldwide. A venomous snake hiding in South American forests helped inspire medicine, now sitting inside ordinary bathroom cabinets across the planet. The irony feels almost impossible to ignore. A chemical evolved to kill prey became part of treatment designed to keep human hearts alive longer. And that may only be the beginning. Researchers now study venom from spiders, scorpions, cone snails, jellyfish, sea anemones, and countless other creatures, searching for molecules unlike anything humans could easily invent from scratch. Evolution has already conducted the experiments for us across hundreds of millions of years. Every toxin surviving today represents chemistry refined through relentless biological trial and error. Some scientists describe venom libraries almost like hidden pharmaceutical vaults scattered throughout nature. The cone snail became one of the most famous examples. Slow-moving and visually beautiful, it hardly resembles a medical breakthrough waiting beneath coral reefs. Yet, inside its venom are compounds so specialized that certain molecules can target nerve pathways with astonishing precision. One cone snail toxin eventually inspired the development of a powerful pain medication used for severe chronic pain cases. And what makes that especially fascinating is how differently it works compared to opioids. Modern pain medicine faces enormous challenges. Opioids can be highly effective, but they also carry risks of addiction, tolerance, and dangerous side effects. Cone snail compounds offered researchers an entirely different approach, not simply dulling pain broadly, but interrupting specific nerve signals more directly. Nature had already solved part of the problem in silence beneath the ocean. And perhaps that is what makes venom research feel almost philosophical at times. Humans often think of evolution as chaotic or cruel, yet venom reveals astonishing biochemical elegance hidden beneath survival itself. A spider does not understand neuroscience. A scorpion does not study molecular biology. And yet their toxins interact with the nervous system so precisely that scientists continue learning from them. Some venoms target ion channels, microscopic gateways controlling electrical activity in nerves and muscles. Others affect clotting proteins, inflammation, or cellular communication pathways. In medicine, specificity matters enormously. A treatment affecting only the intended system can reduce damage elsewhere in the body. Venom evolved around specificity from the very beginning, because predators wasting energy on inefficient toxins simply survived less effectively over evolutionary time. And some of the most promising discoveries may involve cancer research. Certain scorpion venom compounds appear capable of binding preferentially to specific tumor cells under laboratory conditions. Researchers continue investigating whether these molecules might eventually help surgeons identify cancers more clearly or deliver treatments more precisely. Important questions remain unanswered, and many approaches are still experimental. But the direction itself reveals how dramatically humanity's relationship with venom has changed. The same creatures once viewed only as symbols of death are now studied as potential partners in healing. Even snake venom, historically feared across civilizations, may contain compounds useful in stroke treatment, anticoagulation research, and cardiovascular medicine. Some toxins prevent clotting, others encourage it. Some influence blood vessel dilation. The body systems venom evolved to manipulate happen to overlap with many systems doctors struggle to control medically. Nature discovered biochemical shortcuts long before humanity built laboratories. And perhaps nowhere does this become stranger than in the study of paralysis itself. Neurotoxins, capable of stopping muscles from moving, may also help scientists understand diseases involving nerve degeneration or muscle disorders. By examining exactly how toxins interrupt communication between nerves and muscles, researchers gain insight into how those systems normally function in the first place. Venom became a map. A dangerous one, certainly, but also an extraordinarily detailed guide to the hidden architecture of life. Because toxins reveal vulnerabilities the body usually hides from conscious awareness. How nerves transmit signals, how muscles respond, how blood clots, how cells communicate distress, how pain travels. Venom exposes those systems by interfering with them. And strangely, some scientists believe humanity has explored only a fraction of the medical potential hidden inside Earth's venomous species. Millions of organisms remain poorly studied, especially in rainforests and deep oceans where biodiversity remains enormous. Entire molecular libraries may still exist undiscovered beneath coral reefs or hidden inside creatures humans rarely encounter. That possibility becomes even more astonishing when researchers consider how flexible venom evolution appears to be. Some species produce dozens or even hundreds of compounds simultaneously. Venom composition may shift across geography, age, diet, or environmental pressure. Evolution keeps experimenting continuously, creating biochemical variations no laboratory would likely invent independently. Nature does not design toxins for human understanding. It designs them for survival. Yet, survival chemistry sometimes overlaps perfectly with medicine. Of course, transforming venom into safe treatment is extraordinarily difficult. A useful molecule may exist alongside many dangerous ones. Dosage becomes critical. Delivery methods matter. Side effects require years of study. What works inside a petri dish may fail inside the human body entirely. There is no simple path from fang to pharmacy. And still, researchers continue searching, because every successful discovery changes how humanity sees venom itself. The old image of poison as purely destructive begins collapsing. Venom becomes more complicated, less like evil chemistry and more like concentrated biological information, molecules carrying instructions evolution refined over unimaginable time. Some scientists even compare venom research to decoding messages written by nature. A spider's toxin reveals what prey nervous systems fear most. A snake's venom exposes weaknesses inside circulation and muscle control. A cone snail's compounds demonstrate astonishing neurological precision. Each venom tells a survival story, and hidden within those stories may be future medicine humanity has not discovered yet. That idea feels almost poetic in a strange way. The same earth producing danger also produces healing through the very same mechanisms. Evolution does not separate destruction and creation as neatly as humans prefer. A toxin causing paralysis in one context may relieve suffering in another. The difference lies in understanding. And perhaps that is why venom research continues capturing scientific imagination so powerfully. It forces humans to confront how little we truly know about the natural world, even now. Tiny animals hidden beneath rocks or drifting through dark ocean currents may contain chemistry capable of changing medicine forever. Not through magic, not through miracles, but through molecules shaped patiently across millions of years while humanity did not yet exist. Tonight, somewhere in a rainforest, desert, cave, or coral reef, another venomous creature continues carrying compounds science has never studied. Its toxins evolved only to hunt, defend, or survive. And yet, inside that invisible chemistry may already exist the foundation for future painkillers, cancer treatments, heart medications, or neurological breakthroughs waiting quietly inside nature itself. Hidden in the same fangs humanity once feared beside ancient fires in the dark. Somewhere beneath the forests of South America, a snake waits motionless in darkness, while heat from a nearby animal slowly enters specialized organs inside its face. The prey has no idea it has already been detected. To human eyes, the forest appears almost completely black, but the snake is not hunting with ordinary sight anymore. It is reading heat itself. And hidden inside its fangs is chemistry refined across millions of years to shut down another living body with terrifying precision. The deeper scientists study venom, the stranger the questions become. Because venom does not behave like a simple weapon. It behaves more like an evolving language between predator and prey. A biochemical arms race unfolding silently across Earth for hundreds of millions of years. And some researchers suspect humanity still understands only fragments of it. One of the biggest mysteries involves a deceptively simple question. Why did venom evolve so many different times? Snakes evolved venom. So did spiders, scorpions, jellyfish, cone snails, insects, fish, octopuses, and even a few mammals. These animals are separated by enormous evolutionary distances. Many share no recent common ancestor carrying venom systems at all. Yet nature repeatedly arrived at the same solution. Again and again, evolution discovered that invisible chemistry could overpower strength, armor, speed, or size. That pattern suggests venom may represent one of the most successful survival strategies ever created. But it also raises a disturbing possibility. If evolution repeatedly invents venom under pressure, could entirely new venom systems still be emerging right now? Some scientists believe the answer may be yes. Venom is not static. It changes continuously. Researchers have discovered regional differences in venom composition even within the same species. Snakes separated by geography sometimes produce chemically distinct toxins because prey differs between environments. In other words, venom evolves locally. A predator hunting rodents may slowly develop different toxin profiles than relatives hunting birds, amphibians, or fish. Over immense stretches of time, survival pressures sculpt chemistry itself. That means venom is not ancient history. It is still evolving tonight. And perhaps nowhere does that become stranger than in the relationship between predators and resistance. Nature rarely allows one side to dominate forever. Some ground squirrels in North America appear to possess partial resistance to rattlesnake venom. Mongooses evolved unusual receptor structures, helping them survive certain neurotoxins. Honey badgers show remarkable resilience against bites that would severely injure many other mammals, which forces venomous predators to keep adapting in return. The result resembles an invisible biological arms race stretching across millions of years. Stronger venom selects for better resistance. Better resistance selects for more specialized venom. Evolution escalates silently, generation after generation. And some researchers wonder how far that escalation could eventually go. Could future venom become dramatically more complex? Could climate change, habitat shifts, or environmental pressure alter toxin evolution in unexpected ways? No one fully knows. But there are already hints that venom systems may respond faster to ecological change than humans once assumed. Even more mysterious is the possibility that some extinct predators may have carried venom too. For years, paleontologists debated whether certain dinosaurs or ancient reptiles possessed venom delivery systems. Evidence remains controversial in many cases, but species like Sinornithosaurus sparked discussions because of unusual grooves in teeth resembling primitive venom channels. The debate continues. Some researchers argue such structures may have supported mild venom systems. Others believe alternative explanations fit the evidence better. The fossil record rarely preserves soft tissues clearly enough to settle these questions completely. But the idea itself changes how prehistoric Earth feels. Imagine forests where feathered predators delivered toxic bites instead of relying purely on physical injury. Imagine ancient ecosystems shaped partly through invisible chemistry, rather than brute force alone. It may have happened, or evolution may have experimented briefly with venom in certain lineages before abandoning it entirely. That uncertainty is what makes venom so fascinating scientifically. The deeper humans investigate it, the more evolution begins looking less predictable and far more experimental. And perhaps the strangest mysteries involve toxins humans barely understand even today. Some venom compounds create effects so specific they almost seem engineered. Certain spider toxins target individual ion channels with astonishing precision. cone snail venoms may contain hundreds of unique compounds working together simultaneously. Some marine toxins affect pain pathways so intensely that victims describe sensations beyond ordinary language. Why would evolution produce chemistry this complex? One possibility is that venom systems evolved gradually through endless small refinements over geological time. Another is that ecosystems themselves reward specialization so strongly that toxins become increasingly intricate automatically. But some researchers suspect there may be deeper evolutionary advantages humans do not yet fully recognize. Pain itself, for example, remains mysterious. Why do certain venoms cause agony far beyond what seems necessary for survival? In some cases, intense pain likely functions defensively by teaching predators unforgettable lessons. Yet, certain toxins create suffering so extreme that scientists still debate exactly why such intensity evolved. Perhaps pain alters behavior more effectively than injury alone. Or perhaps some effects humans experience are accidental side consequences rather than intended evolutionary outcomes. Nature does not optimize for human understanding. And then, there is one of the most unsettling possibilities of all. What if humanity has encountered only a tiny fraction of Earth's venom systems? Rainforests still contain species undiscovered by science. Deep oceans remain largely unexplored. Underground cave ecosystems isolate strange organisms for millions of years. Entire branches of evolutionary experimentation may exist far beyond direct human observation. Some scientists suspect many mild venom systems remain hidden simply because researchers were never looking carefully enough. Certain lizards, once considered harmless, later revealed venom-related traits. Saliva, digestive enzymes, toxins, and true venom may blur together more than traditional biology categories suggest. The boundary itself may be artificial. Evolution does not care whether humans label something venomous or poisonous. It only rewards survival advantages. That realization becomes even stranger when considering extraterrestrial life. If life exists elsewhere in the universe, would venom evolve there too? At first, the question sounds almost absurd. Yet, venom represents a surprisingly logical solution to survival problems. If alien ecosystems contain predators and prey, competition and biological conflict would likely emerge eventually. Chemistry might become weaponized there, just as it did on Earth. Some astrobiologists speculate that biochemical warfare could be nearly universal wherever complex life evolves. Not because evolution seeks cruelty, but because efficiency survives. And perhaps the most haunting mystery is how venom intersects with human vulnerability itself. Humans dominate Earth through intelligence, cooperation, and technology. Yet tiny animals carrying microscopic quantities of toxin can still overwhelm the body frighteningly fast. Venom exposes how fragile biological systems truly are beneath the illusion of control. A few molecules interrupt breathing. A few molecules disrupt the heart. A few molecules silence muscles. Evolution discovered hidden weaknesses inside life long before humans recognized them scientifically. And despite all modern medicine, some toxins still remain difficult to treat effectively. certain jellyfish venoms, rare snake species, deep marine toxins barely studied at all. There are still compounds entering hospitals that doctors understand only partially. Nature remains ahead of us in some places. At the same time, researchers continue uncovering astonishing medical potential hidden within these same toxins. Venom molecules may eventually help treat chronic pain, cancer, neurological disorders, clotting diseases, or autoimmune conditions. Which creates one final contradiction. The deadliest chemistry on Earth may also become some of humanity's most valuable medicine. Perhaps that duality exists because venom reveals something fundamental about evolution itself. Nature does not divide creation and destruction cleanly. The same molecule capable of causing suffering in one context may preserve life in another. Meaning depends on circumstance. A fang injecting venom into prey creates death. A scientist isolating that same compound inside a laboratory may create treatment instead. And still, countless mysteries remain unresolved. How many venom systems evolved and disappeared before humans existed? How many still remain undiscovered beneath the ocean? How far can toxin evolution continue changing? Could entirely new biochemical strategies emerge in the future? No one truly knows. Tonight, somewhere beneath jungle canopies, inside coral reefs, under desert stones, and deep within black ocean trenches untouched by sunlight, evolution continues, conducting experiments in silence, exactly as it has for hundreds of millions of years. Some of those experiments drip from fangs. Some hide inside translucent tentacles. Some may not even be recognized by science yet. And perhaps the most unsettling realization of all is this. Humanity studies venom as though it belongs to the past, while nature may still be inventing new forms of it right now in the dark. When humans imagine dangerous predators, they usually picture noise. Roaring, chasing, teeth crashing through bone somewhere in the dark. But the natural world rarely works that way. Some of the deadliest creatures on Earth move through silence so complete that prey often never understands what happened at all. No dramatic attack, no warning echoing through the forest, just a small movement beneath leaves, a drifting shape beneath water, or the brief sensation of contact before invisible chemistry begins moving through the body. And perhaps that is the final truth hidden inside the world of venom. The creatures carrying it are usually not conquerors. They are survivors. Somewhere tonight, beneath desert stones cooling after sunset, a scorpion waits, motionless outside its burrow entrance. In rainforest branches, a pit viper coils so perfectly into shadows that even experienced hikers could walk past without seeing it. Far below the ocean's surface, translucent tentacles drift silently through black water older than human civilization itself. None of these creatures are searching for conflict. Most are trying desperately to avoid being noticed. That may be the strangest contradiction in the venomous world. Humans often describe venomous animals as aggressive monsters, yet evolution usually shaped them towards stillness instead. Venom works best when energy is conserved. A predator relying on toxic chemistry does not need endless pursuit. It does not need loud displays of strength. It only needs patience. And patience changed everything. A lion survives through force. A wolf survives through cooperation. But venomous creatures often survive by becoming nearly invisible inside the environment itself. Camouflage, silence, immobility, and precision replaced raw power. Evolution discovered that remaining unnoticed could be more effective than domination. Some venomous snakes barely move for hours while waiting beside animal trails. Trapdoor spiders remain hidden underground until vibrations reveal prey above them. Stonefish disappear so completely into reefs that they resemble coral-encrusted rock rather than living animals. The attack begins only when survival requires it, and sometimes not even then. Many venomous species avoid using venom unless absolutely necessary, because producing toxins is biologically expensive. Venom requires proteins, metabolic energy, specialized glands, and constant replenishment. A wasted strike carries consequences. A snake injecting venom defensively into something too large to eat may leave itself vulnerable later during hunting. So evolution rewarded restraint. That may explain why warning systems evolved so frequently among venomous animals. Rattlesnakes announce themselves. Cobras spread hoods dramatically. Bright poison frogs advertise toxicity through color. Even tiny blue-ringed octopuses flash glowing patterns before biting. Nature repeatedly created signals saying the same thing. Please leave. The goal is often escape, not battle. And perhaps humans misunderstood venom partly because fear distorted the picture. The moment a venomous animal appears, attention narrows instantly toward danger. But the animal itself is usually trapped inside the same fear response. It does not understand human intentions. It only recognizes something enormous approaching suddenly through its environment. In many cases, humans and venomous creatures are frightening each other simultaneously. Yet despite that mutual fear, something about venomous animals continues pulling human curiosity toward them almost hypnotically. Zoos display cobras behind glass. Nature documentaries linger on close-up shots of fangs and stingers. Entire mythologies formed around snakes, spiders, and poisonous creatures across civilizations separated by oceans and centuries. Perhaps because venom exposes something deeply unsettling about life itself. Strength is not always what matters most. A tiny spider can overpower prey far larger than itself. The jellyfish, without a brain, can stop the human heart. A small amount of invisible chemistry can interrupt breathing, memory, movement, or consciousness. Venom reveals how fragile biological systems truly are beneath the illusion of control. And evolution built those systems patiently over unimaginable stretches of time. Long before cities existed, venomous creatures were already shaping ecosystems quietly in forests, deserts, reefs, and rivers worldwide. They regulated prey populations, influenced animal behavior, forced adaptations, created evolutionary pressure, pushing entire species toward resistance, caution, or avoidance. Invisible chemistry became part of Earth's balance. And in some ways, humans joined that balance late. Our species evolved in landscapes where venomous snakes, spiders, and toxic plants already existed. Fear of hidden danger may have sharpened awareness itself. Some researchers suspect early humans surviving in dangerous environments became unusually attentive to movement patterns associated with snakes or insects because noticing quickly carried survival value. If true, traces of that ancient awareness may still remain inside modern nervous systems. A sudden shape beside the footpath, movement beneath tall grass, a spider crossing a wall late at night. The body reacts before thought fully forms. Yet over time, humans did something unusual with that fear. We began studying it. Venom moved from mythology into science. Ancient terror slowly transformed into toxicology, neurology, evolutionary biology, and medicine. Researchers discovered toxins targeting nerves with astonishing precision. Compounds evolved to kill prey eventually became tools helping scientists understand pain, blood pressure, clotting, and disease. The same chemistry once associated with death became part of healing. And that transformation says something important about humanity too. We are one of the few species capable of turning fear into curiosity instead of permanent avoidance. Still, nature continues holding on to mystery. The deep ocean remains largely unexplored. Rainforests still contain species undiscovered by science. Some venom systems may exist in animals humans barely study or do not yet recognize as venomous at all. Evolution continues experimenting in silence beyond direct observation every moment. And perhaps that uncertainty matters, because the world becomes smaller emotionally when humans believe everything is already understood. Venomous creatures remind us that Earth still contains hidden systems operating independently from human control. Entire biochemical wars unfold constantly beneath leaves, under coral reefs, inside caves, and across deserts without human awareness. A spider waiting inside a web, trembling with vibrations. A cone snail drifting slowly over coral beneath moonlit tides. A pit viper sensing body heat in darkness deeper than sight. Ancient survival strategies continuing exactly as they did before human history began. And perhaps what makes venomous creatures feel so cinematic is not simply danger, but silence itself. Silence forces imagination to work harder. You do not hear venom moving through blood. You do not hear toxins interrupting nerves or muscles. The attack unfolds internally, invisibly, beneath the threshold of ordinary senses. Venom transforms the body quietly from within, while the surrounding world may remain perfectly calm. Wind still moves through trees. Ocean currents still drift through reefs. Night insects still sing beneath stars. Nature rarely pauses for violence. It simply continues. And maybe that is the final lesson hidden inside the venomous world. Humans often imagine nature as emotional, cruel, angry, merciful, evil. But venomous creatures reveal something colder and perhaps more beautiful at the same time. Nature is efficient. Venom was never created to torture or terrify. It emerged because evolution repeatedly discovered that chemistry could solve survival problems elegantly. Small predators could hunt larger prey. Vulnerable animals could defend themselves without physical strength. Energy could be conserved. Risk could be minimized. What humans experience as horror, evolution experiences only as adaptation. And still, despite all scientific understanding, something ancient remains inside the feeling these creatures create. A king cobra rising from grass still feels mythological. A scorpion glowing beneath ultraviolet light still feels unnatural. A jellyfish drifting silently through dark water still resembles a ghost more than an animal. Science explains mechanisms, but mystery survives. Tonight, somewhere beneath rainforest canopies, desert sand, mountain stones, and black ocean depths untouched by sunlight, venomous creatures continue moving through their hidden world exactly as they have for millions of years. Most will never encounter humans. Most will never attack anything larger than prey. Most will disappear silently before ever being seen. And perhaps that is the strangest truth of all. The world of venom was never really built around humanity. We simply wandered into it late, carrying flashlights, fear, and curiosity into an ancient silence that had already been waiting there long before we arrived. Thanks for exploring the strange world of venom with me tonight. If you enjoyed this relaxing journey, don't forget to subscribe to Sleepy Secrets for more calm mysteries to fall asleep to. And before you drift off, leave a comment below telling me what topic you'd like to explore next. Wishing you a peaceful night, good health, good luck, and a deep, restful sleep tonight.